Hello, everyone. Yeah, I'm going to attempt to explain category theory to biologists in 15 minutes. Okay. So what is category? I may be done in less than 20 minutes. Like, I don't think I'm going to use my, okay. What is category theory? So I think of it kind of like the math of math. Math fields are ways of accounting for repeatable phenomena. So maybe you have two fields of cows and a fence between them, and you remove the fence, and that's plus. You have a grid of 5 by 7, and there's 35. That's times. So, but arithmetic is how you account for, say, the flow of quantities in finance. You're going to add numbers in your spreadsheet. Hilbert spaces are how you account for the states of elementary particles in quantum mechanics. If you want to give an account of that somebody can understand and use, you're going to use Hilbert spaces often. Probability distributions account for likelihoods in game theory. If you want to make maps, the way you give accounts of it, you're going to use angles, you're going to use distances, and that's geometry. So mathematical fields are these ways of accounting for different phenomena. And so roughly math I think of as like stable, communicable, compressible thought patterns. So you don't need like a huge, you can write it down and then it's compressed in the sense it's short, and it's also repeatable and stable so that I can solve a differential equation here and someone else can solve a differential equation there, and we can like put our answers together when we're forming the rocket ship or whatever. So it's communicable, it's stable, it's not, 2 is not different this year than it was last year. So it's very, that's a quality of math. So each of these fields was invented by somebody, like Newton invented calculus, right? To understand, the rates of change of different things. And so that's what happens in math. Like in grade school math, you learn somebody else's game, but in like PhD math, you invent your own game, kind of. So we're trying to track some phenomenon, the motions of something or something, with some symbols, where like when I put that plus, it is the same as removing the fence, right? That's what the symbols do. They're supposed to tell you, if I do this operation, this will happen in the phenomenal world, but phenomenological world. So that's kind of the idea. And I need to say that because if I want to tell you what the math of math is, then I have to like kind of repeat that, right? So category theory does this same thing for math. So it was invented in the 1940s to formalize a common notion that they were using a lot back then called natural. They would say that this transformation is natural, but they had not defined what natural meant. And so it was just like one of the most cool words in the world, natural, was being used by mathematicians, and they didn't know what it meant. So category theory, they needed to invent categories, then functors, then they could define natural transformations at like level 3, but that was kind of the point of it. And so category theory connects disparate areas of math, and it has been used to prove major conjectures. These days, it's kind of even used to just state what you want, because you can't compress things enough using non-category theory to like say the cool phenomenon that you want to talk about. So it finds and distills the repeated phenomena from throughout math, just like these mathematical fields find repeatable phenomena throughout nature, let's say. So the main phenomenon that I think category theory distills and formalizes is, in some sense, maybe the power of analogy. So analogy, you might think of as like a weak thing that you just use for your mind or something. But it's actually something that we use all the time in all of science. We're using it over and over. So that's a phenomenon that you could try to say, oh, is there anything about this phenomenon that is repeatable, stable, compressible? And so what is analogy? It's kind of a similarity of structure across a difference of content. Like my love is like a red, red rose. I mean, my love, the content of one is nothing like the content of the other. But the structure, well, I don't know if the structure is the same. Maybe she's thorny. I don't know. Okay, so unifying repeated phenomena. I don't know. I don't actually get that. I should use a metaphor I get before I use it. Unifying repeated phenomena across math lets you actually transport theorems. So when I say that this is the analogy, it's rigorous enough that you can take a theorem from one area of math, say group theory, and transport it into another area of math altogether, like topology. And that transportation of theorems is like a proof. It's a full proof. And I think of category theory as like a conceptual stem cell, in that it can differentiate into a huge variety of different forms. So first of all, it differentiates into all forms of pure math, like algebra, topology, logic, number theory, differential equations. But it also differentiates into like databases and knowledge representation, or functional programming languages with Cartesian closed categories, or dynamical systems and fractals, which might seem different, but there's something in common between those two. Shannon entropy, taxonomies, chemical reaction networks, quantum processes, compartmental models, deep learning, all these things, you can talk about them in a category theoretic way. And what that means is that they kind of can work together coherently. You can make analogies between them, like the dynamical systems and fractals one that I mentioned up there. So now you might counter like, well, a theory that explains everything explains nothing. So category theory often will be complained about as like, isn't that just a language? Does it actually do anything? And first of all, I love language. It's what I'm using right now. And like a really good language can help a lot. But second of all, I would counter that objection of Popper if he was saying this in two ways. One, couldn't you make that same objection about mathematics? It's the basis of hard science. It's used everywhere. And category theory, like math, it explains and models and formalizes many things, but that doesn't mean we should conclude that math explains everything and hence explains nothing. That's not what that's doing. So I think what's happening here is like, one way to think about it is stem cells don't do real work until they differentiate. So you're not going to actually use category theory in your field of biology, just basic category theory. You're going to find the one that actually fits. You're going to pick the one little part of category theory that would fit, and then you would find the right terminology, the right computational techniques, etc. And then eventually you get something that can actually do work. But so I think that's it's got all these different things that it can do, but you have to pick one to actually do that one thing. And I think that the unified origins of category theory, why I'm calling it a stem cell, is that not only does it differentiate into things, but because it's all coming from the same like basic structure, you get this interoperability of the things that it does make. And so that's what I think we need for interdisciplinarity, is this ability to interoperate and yet talk about different things. And I think that category theory is the gateway to pure math. Like I think it's humanity's most powerful thought compression language. It's designed to transport theorems from one area to another, from topology to algebra. But it's revolutionized pure math since the 40s. It's greatly influenced all corners of math, or at least touched them, and it's gaining influence. And the reason is just that it's such a good compression language. You can say so much in so little. But I think it's becoming a gateway in the sense that if you wanted to learn group theory, I kind of think you maybe should learn category theory in like first, or a little bit of category theory and move into group theory. You want to learn topology, you kind of learn category theory and then move into topology, because you're going to get to see like the common forms that you should be on the lookout for. And just branch out of math. So I want to just give you one taste of it, called operads. It's a framework for formal models of like interfaces and operations, ways of taking things and putting them together to get things. And the danger is that you're going to see this, and everyone I show who doesn't know category theory, this will be what you think category theory is. And that's just because when you have one example of something, that's just what our minds do. So you might assume this is all category theory by the end of this talk, because you haven't seen anything else, but it's not. So it's kind of like just, yeah. So what is an operad? It includes three things. In math, you'd call it objects, morphisms, and composition, but I'm going to call them interfaces, like things that interfaces, some kind of like whole or something, or variable, arrangements, ways of putting these interfaces together, and that those arrangements nest in some way. So if you wanted to tell me an operad, you would tell me all the interfaces that you're going to consider. Is an interface an input-output, the input symbols and output symbols of something? Is an interface the dimensions of a tensor or array? Is an interface like, what is an interface? Is it the before and after conditions of something? You just tell me what is an interface, and you tell me how do you arrange them. If I have some before and after conditions, can I take those like 5 different before and after conditions and make one before and after condition? Maybe I'll make sense of that in a minute. Or if I take 5 different input-output types, can I put them together into something that has a single input-output type? And I'll explain all of what I'm saying in a minute, but that's the arrangement part. And I'm going to use this color coding. Hopefully I'll remember in these slides, blue will be the interfaces, red will be the arrangements. And nesting is that if you have arrangements and arrangements, you should be able to turn that into one big arrangement. Like if you have little logic gates, NAND gates inside of a logic gate, and you have logic gates inside of an adder circuit, and you have adder circuits inside of a CPU. In principle, you could, well, in reality, you could take that CPU and like notice that it was all NAND gates or, you know, transistors at the bottom. That wouldn't be useful for analysis, but it's useful to know that you didn't add anything from transistor to CPU. All you did was arrange them in interesting ways. It's useful to know that our bodies at the end are just elements, carbon and nitrogen. Even if you don't want to like go down to that scale, you know at least you can, and that you're not adding anything additional. So operad 1 is recipes. Maybe an interface is a step, like the step called prepare vegetables or do carrots. And an arrangements is some steps that constitute a step. So someone says, how do I prepare veggies? Oh, just do the carrots and then roast the Brussels sprouts. And then someone else says, well, how do I do the carrots? And well, wash the carrots, peel the carrots, and chop the carrots. And the nesting, so that's like the arrangement is that like arrangement in time, kind of arrangement of steps that like the output of one step, a washed carrot, is the input of the next step, peel carrots or something like that. And then the nesting is that you can prepare the vegetables by washing the carrots and then peeling the carrots and chopping the carrots and roasting the vegetables. So like that you can take recipes and like detail out what each recipe is. Like to chop the carrots, you like take your knife up and then you put it down or whatever. And like you can at the end just make this go all the way down to the most basic operations. So recipes form an operad. Here's a recipe for shakshuka that I got from my friend.
Oh my gosh.
There's an operad for hierarchical protein materials. So I was working with someone named Marcus Buehler, and we were making hierarchical, or like a programming language for hierarchical protein materials. And why would you want them? Well, they include protein materials are like your skin, say, so collagen. So it's stretchable, breathable, waterproof. Like that's an amazing material that they don't know how to make in the lab. And not only that, but you eat like, you know, carrots and hamburgers, and you make this material. Like that's, or spiders eat flies and they make something stronger pound for pound than steel. So like we want to know that it's not that they're making titanium. They're not making one element and then repeating it. They're making something with such amazing structure that structure is stronger than steel. So material scientists really want to know how you do that. And so our idea was that a protein is an arrangement of simpler proteins. So we have protein as the interface, and then what do you need to arrange them together to make bigger proteins? So you could pretend that amino acids are proteins. They're not, but you could say like, okay, the atomic protein is the amino acid. Its interface is, I forget the words now, carbolic side and amine. No, I don't know. Sorry, I've forgotten so much since then. So you can arrange these in series. You can arrange them in parallel with hydrogen bonds. You can put them in helices. You can put them in double helices, etc. So here's collagen as a nested structure. It was like this. It was an array of fibers. Each fiber is a triple helix that you see there. Each helix is actually spinning, like going the other way. Each of those strands in the triple helix is actually a helix going the opposite direction. And then each unit of that is an amino acid. So you can build up bigger and bigger structures by arranging smaller structures. Operad 3, which I had on the board yesterday, is wiring diagrams. Here, the interfaces are those boxes with ports. So X11, I don't know if I have a laser on this thing. Maybe not. X11 is an interface. X12 is an interface. It has 2 input ports and 2 output ports. But Y1 is also an interface. Y1 has 2 input ports and 2 output ports. Y2 has 1 input port and 2 output ports. And then Z is an interface, has 1 input port and 2 output ports. And so there's an arrangement of Y1 and Y2 inside of Z where you don't get to look inside Y1 and Y2. They're like black boxed away. But you can see that Y1 is connected to Y2 and Y2 feeds back, blah, blah, blah. But then you could also zoom into Y1 and see that it was also an arrangement of smaller things, and you could keep going down as far as your theory gives you. And when you nest that, like nesting some things inside things, you get this, which would be harder to maybe think about, or you could cluster in many different ways. But however you cluster it, there's an associative law in operads, just like parentheses. The clustering here is kind of like parentheses instead of like just, So no matter how you parenthesize it, you get the same answer. That's the requirement if you want to tell me you have an operad, you have to tell me that you have interfaces, arrangements, nesting, and that they're associative. And then there's something called algebras for operads, which is like assigning the meaning. Before these things, like what does it mean? What's in those boxes? Like, tell me what's in the boxes. Well, there could be anything in those boxes as long as they work according to the like rules of according to these arrangements. What does that mean? So what can go in the boxes? You could put partially observable Markov processes in the boxes where inputs come in and then some state is changed probabilistically, and then out comes some function of the internal state that you don't get to know, or even a stochastic function of the inputs, the internal state. And the point is that if you had those in each of those boxes, each of them getting inputs, changing their internal state, sending stuff out, and that the thing that they're sent out was sent into something else as the input, then the whole thing would also be a partially observable Markov process where the states would be like the products of the states inside. So you'd kind of keep track of all the states, a tuple of all the states, and you could just update them and you would know exactly what to do. So that's why it's that's an algebra. This like algebra means like these boxes are the variables, and what can go in a variable instead of a number is a partially observable Markov process. Like something, or what goes in there instead of a variable, instead of a number, is a tensor. You could put like inside of this thing, you could put a three-dimensional tensor, like a three-dimensional array of numbers. And if you put a tensor in each one of these, this would be called a tensor network. And getting the total outside tensor would be called tensor contraction. So that's another algebra for the same operad. Another one is continuous dynamical systems with inputs and outputs. So you have like some dynamical system, a system of ODEs, but those ODEs can depend on a parameter, and that parameter is time varying and coming in from somebody else. And you're also exporting a function of your state. And that function of your state is some like projection of your state that's being sent to somebody else as their parameter. And so that's something, if each one of those was doing that, then the whole thing would also be doing that. So that's called an algebra of this system. Right, I think I said it here. If the box was like AB, then the system of ODEs, X is a vector here. X could be any, X1 through Xn, and it's F of X1 through Xn, comma, the input state, and some kind of readout B that is a function of the state. And if you had that for each of those boxes, if one of the boxes had two inputs, then it'd be like F of X, comma, A, comma, B, or something like that. So then you would get a new dynamic ODE from old, which if you go back to like undergraduate differential equations class, we probably had like a tank full of brine, like sending some, and some salts coming in and stuff. And that we were already doing that. We were just doing that with like one tank. We were doing like a single one box and then one other box. But the point is that there's a formula where you could just get all of it at once instead of kind of that simple thing. But there's also, as I said, an algebra of tensors. You could put tensors in the boxes, and you could construct new tensors from old. And in fact, the fixed points gives you a natural, in the sense that I said in the beginning, a natural transformation from the ODE system, this one, to this one. You could take your ODE and look at a tensor that says for every input, comma, output, put the number of steady states or equilibria in as your number at that coordinate. Like maybe there are no steady states. Sorry, let's say you're getting in 5 and you're reading out 7 and you're in a steady state. Reading like as long as 5's coming in, I'll be in the steady state outputting 7. Then you put the number of states like that you put in your tensor. Then the natural transformation says that if you take this whole system of ODEs and combine them into a big ODE and then take the steady state tensor of that, that is the same thing as taking the steady state tensors of each of them and then doing the tensor contraction and getting one tensor. So like you can either calculate the steady states first and then contract, or you can combine your ODEs and then find the steady states and you get the same answer. And that's that's an example of a natural transformation in the sense I said that Eilenberg and MacLean, who invented category theory, were looking for. So that's my whole talk. Category theory, like all math, is a language and tools for kind of tracking observable phenomena. Like we're trying to see throughout math, like intersections, product, greatest common divisor, those are somehow the same. Like the greatest common divisor of 6 and 8 is 2. Like that has something to do with intersecting sets. What does it have to do with it? Well, category theory will tell you what it has to do with it. It's trying to track that there is the same story over and over again throughout math. And it's giving you the framework for operating on and composing relationships between things. And it lets you compare frameworks so that these frameworks can cross-pollinate. So if you want to read more, if you're kind of on the math side, I think Leinster's book, Basic Category Theory, even if you're like don't know much math, but you like math a lot, I think that's a good one. If you know a lot of math and you want to learn category theory, maybe Emily Reel's book, but I didn't put that up, called Categories in Context. If you like applications, I guess I'll plug my own book, Invitation to Applied Category Theory. And if you like kind of philosophy and vibes and like stuff like that, but you like kind of nicer and easier on you, Eugenia Cheng's Joy of Abstraction and How to Bake Pie are good books. So yeah, thank you.
Thank you. Any quick questions for David? So yes, we'll take 2 questions again here.
So when arrangements are nested inside one box, does it?
Sorry, can you say again?
When arrangements are nested inside one box, does it always go like forward?
Forward? What goes forward?
From input of like the first one, you put it. No, the output of the first one you put as input in the second one.
So is it always bottom up? She's asking.
Yeah.
In these in a tensor network, for example, there would be no input, no output. These would just mean you could do input output, but you could kind of think of them as just arrays of numbers and you don't care at all. Are you talking about the specific algebra of ODEs?
Yeah, can you go like one slide before? No, the one after. Yeah. So here you take the
small
like input of y1 to y2, but then for like output of y1 to y2, and for like input of y1 you again need value of y2.
Yeah, so for one input of y1 you need a value of y2. Is that what you said?
Yeah.
Yeah.
But then for one input of y1 you need value of y2, and for one input of y2 you need value of y1.
Yeah.
It's just like circular.
It's circular. It's feedback kind of. Yeah.
Yeah.
So yeah, that can
You
happen.
start with like one initial value and then go into.
Well, if all of them are operating simultaneously, if you have lots of cells or something talking to each other, they're all working all the time. So this input is just the last moment's output of this one.
Okay.
So yeah. At every moment, you could think, okay, send out your signal. Then everybody sends their signal. They all arrive at the inputs, and then they can process the state and go again.
Then we had one other question at the back. I think, yes, you.
I want to say thank you for sharing those resources, and just to let people know the Leinster one is on archive. So it's.
Oh yeah, the Leinster one is on archive. So is mine. I don't know if Eugenia's is on archive.
Okay.
Yeah.
Cool. My question was, you said that we should be teaching, or we should learn category theory before topology or group theory. And I'm just curious, is there any university that does that order?
I don't think so.
That's weird.
No. There are there are linear algebra textbooks that are like Axis, I think it is like taught from a category theory point of view without saying it. There's like a topology book called there's a topology book by Tyden A. Bradley and other people that's like written from a category theoretic point of view. So I think it's more common to start to try to write things in that way, but you're right. I mean, no one does it that way. In fact, most universities don't even have a category theory class at all, even in grad school, because I don't know, you're just supposed to pick it up on the streets, I guess. It's 80 years old.
Okay, I guess we will take one more question.
Sorry, just a comment on what they're saying. So at my university, they do have a category course, and it does not assume algebra. It's a disciplinary communications course.
Nice.
So it is taught in a way that doesn't assume any prior knowledge.
That's great.
So that's Nick Gursky that does that. So maybe
Great.
people
That's awesome.
about that.
Really happy to hear that.
Thank you, David.
Thank you.